Hello, everyone. Welcome to this week's Ezra Systems seminar, and we'll have Dr. Zheyu to give a presentation. But before he starts, I would like to introduce him to you. So, Dr. Zheyu joined the School of Chemical Engineering at Oklahoma State University as an assistant professor in 2021. He completed his BS at the University of Minnesota in 2014 and PhD at Purdue University in 2018, both in chemical engineering. Between 2018 and 2021, Dr. Jiang worked as a process development engineer in the small molecule discovery and development group at Dow Chemical and Corteva Agriscience, where he continued to the market launch of Adavelt, the first broad-spectrum picolinamide fungicide products. At OSU, Dr. Jiang's research group focuses on developing new mathematical modeling, optimization, and machine learning tools and system-level insights for advanced separations, industrial decarbonization, digital agriculture, and Industry 4.0. So, Dr. Jiang.
Thank you very much. Thank you very much, Ben, for the kind introduction. And thank you, Dr. Yo, in the audience in Zoom for the warm invitation and for being my host. It's my pleasure to visit Cornell and share some of my thoughts and works on how systems engineering can be used to tackle sustainability challenges associated with modern food and chemical productions. So, first, why do I specifically choose these two topics for this talk as well as for my research focus? It turns out that the reasons are well highlighted in the online description of the scope of the seminar series today, in the sense that systems engineering research can address problems involving large, complex systems and broad implications to the society. So if you think about it, the two sectors that are critical to the standard of living of human society are food and chemicals. To give you a perspective, the average American consumes 1 ton of food every year. And an average American household's food emission are around 8 tons of CO2 equivalents per year. So on the other hand, for our daily life is filled with chemicals, ranging from shoes to the clothes that we wear, to the electronics and plastics that we use, and to the medicines that we take. And the US chemical industry is very diverse, with more than 17,000 products, 11,000 manufacturing facilities, and deep supply chain interconnections. So in my group, we try to tackle some of the long-standing challenges associated with these two important sectors. So in the first half of the talk, I would like to focus on digital agriculture and sustainable food production. I will start by giving you a holistic view of different research problems that my group want to address, followed by focusing on the specific project that we're currently working on. So as you know, by 2050, the global population is expected to reach 9.7 billion. Most of the population growth will occur in developing countries with accelerated economic growth and urbanization. And this leads to a fast expansion of middle class that is embracing a higher standard of living. And these ongoing trends put unprecedented stress on food, energy, and water resources. And specifically, the global food production must increase by at least 70% by 2050. And the global consumption of energy and water will also have to grow by at least 50% between now and 2050. Considering that the current agriculture and food sectors already consume 70 to 80% of the world's freshwater withdrawals, 50% of the habitable land, as well as 30% of the energy produced, the one question that is critical to the sustainable development of human society in the 21st century and beyond is the following. How can we massively increase crop production without putting additional stress on land, energy, and water resources, while at the same time ensuring sustainability for all? So to tackle this grand challenge, we need to conduct highly interdisciplinary and collaborative research to re-examine and renovate all stages involved in the R&D, production, distribution, processing, and consumption of agricultural products, thereby offering data-driven, systems-oriented solutions and insights to the sustainable intensification of global agriculture and food systems. Specifically in stage 1, my group is looking all the way up front at the R&D of seed and crop protection drug molecules productions. In order to meet the market ever-growing needs, it is important for agricultural research organizations to keep innovating and expanding their R&D pipelines. However, despite that, more and more resources are poured in, the pace of innovation in both seeds and crop protection products sectors are among top agricultural companies has been slowing down. And this is mainly because the current innovation approach, which heavily focuses on trial and error experimentation, can no longer catch up with the increasing complexity associated with innovating new seeds and with more favorable traits, as well as synthesizing new crop protection products that are structurally more complex. And therefore, the whole industry must break out of the traditional innovation model and embrace digital transformation to accelerate the R&D process and reduce costs. To facilitate this, my group is trying to, for crop protection sector, for example, my group is developing the state-of-the-art AI-assisted crop protection active ingredient synthesis planning platform and build a smart robotic system to automatically perform organic chemistry synthesis and optimization. In the next stage, I will look into sustainable manufacturing and supply chain of agricultural products. The synthesis of one drug molecule typically involves 10 to 15 chemical steps. Overall, hundreds of kilograms of chemicals, mostly aqueous and organic solvents, are used to produce just 1 kilogram of molecule, resulting in an outstanding carbon footprint. And comprehensive life cycle assessment studies also suggest that most of the carbon footprint is attributed to the production and distribution of these reagents and solvents. And therefore, to minimize energy consumption, total costs, and environmental impacts during agrochemical production and distribution, my group will focus on 2 aspects. The first is to develop new mathematical models and optimization algorithms to decarbonize the active ingredient manufacturing processes. And the second aspect, we're building a sustainable and resilient global supply chain network for agrochemical raw materials and products by formulating and solving a stochastic MINLP that accounts for seasonal variations and uncertainties that are unique to agrochemical industry. In the third stage, I'm planning to develop AI-based precision farming tools to help farmers make rational, informed decisions on which crop they should grow, what the expected crop yield is, and how to effectively monitor and improve crop health. So for example, my group is working on the sensor-based optimization and integrative learning of soil monitoring for sustainable agricultural irrigation, thereby bringing eyes inside the soil. And then lastly, I would like to promote sustainability and identify ways to minimize food waste, water and energy use, as well as carbon footprint during food processing and consumption stages, in which some of the ongoing shifts in dietary habits and cooking preferences have raised several interesting questions. And in particular, we developed systematic life cycle assessment and techno-economic analysis tools to analyze and optimize meal kit delivery market and plant-based meat substituent market. So now let me spend more time on introduce an ongoing project of developing a holistic computational framework to synthesize a low-cost and reliable field-scale soil sensor network that can effectively monitor the impact of adopting marginal quality water for agricultural irrigation. So if we look at where some of the most water-intensive commodity crops, such as soybean and wheat, are grown in the United States, and compare with where droughts take place, you will see, you'll be surprised about how large the overlap is between the 2 maps. And to make things worse, in a lot of these places, the groundwater resources suffer from high salinity content as well. In other words, high-quality fresh water is a scarce strategic resource for agricultural irrigation in the U.S. To address the irrigation water stress, one important water management practice is to reduce freshwater use by adopting non-traditional marginal quality water, such as treated produced water from oil and gas production, and brackish groundwater for agricultural irrigation. And this is especially attractive to large agriculture producing states like Texas and California, regions where brackish water constitutes a high proportion of groundwater resources, such as eastern Arizona, and rural communities in arid regions with limited access to fresh water like southwestern Oklahoma. While most farmers have demonstrated a strong will to adopt marginal quality water for agricultural irrigation, they currently don't actually have adequate information to monitor the impact of agricultural water quality or salinity on crop health and yield. Instead, condition of crop, feel of soil, and personal calendar are the top 3 methods U.S. farmers use to schedule their irrigation activities, which in the case of using marginal quality water will result in soil salinity issues, as crop damage is often noticed long after the salinity development occurs. In addition, only 12% of the irrigated farms in the U.S. have adopted soil moisture sensing, and far fewer farms have ever practiced salinity sensing. And this is because farmers do not know how to strategically place soil sensors in a large field. Instead, they would deploy these sensors randomly, which really limits the capabilities of these sensors. And conventional random deployment of sensors are problematic because it fails to capture the strong spatio-temporal patterns associated with the impacts of root zone, soil moisture, and salinity on crop health and yield. And this leads to significant sensor redundancy and makes the deployment and maintenance costly and laborious. So to tackle these challenges, we propose a unified computational framework to synthesize reliable in-situ soil sensor network that can effectively monitor the impact of adopting marginal quality water on root zone, soil moisture, and salinity levels at field scale. And the key is to systematically incorporate the spatio-temporal dynamics in the data-driven, physics-augmented gray box modeling framework. So to accurately monitor field-wide soil moisture and salinity profiles, we integrate in-situ soil sensing data with physics-based models that characterize the transport of water and solute in soil. So here our goal is to develop computationally efficient numerical methods to accurately solve the coupled transport equations governing the spatio-temporal dynamics of soil moisture and salinity in plant root zone in a large-scale farm. And this coupled PDE system is known to be challenging to solve because of the nonlinearities in the water retention curve and the hydraulic conductivity function that are embedded in the PDE system. So here we have come up with a novel data-facilitated numerical methods that holistically integrated finite volume characterization, adaptive linearization scheme, neural networks, and global random walk theory to produce accurate numerical solutions of coupled PDE system with provable convergence guarantee. One of the novelties of this numerical methods is that we introduce neural networks to learn the mapping and inverse mapping between water pressure head and the number of particles in the global random walk formulation. And we propose a new coarse-to-fine approach that allows high-accuracy numerical solutions to be obtained without the need for high-accuracy, fine-meshed training data. So therefore, this coarse-to-fine approach maintains a very good balance between the computational efficiency and solution accuracy. And we also conducted systematic studies comparing the numerical accuracy and mass conservation performance of different numerical solvers, and showed that ours can accurately reconstruct the underlying physical laws relating to soil moisture, salinity level, water pressure head, and water flux, which are often lost after the discretization process. So once we have this numerical method for solving this physics-based model, it is incorporated in the physics-constrained active learning framework to identify optimal sensor locations in the sequential manner, and as well as in the data-driven, physics-augmented data deep learning framework to construct accurate field scale soil moisture and salinity maps across entire field. So as mentioned earlier, in situ sensors can only measure soil moisture and salinity profiles locally, while deploying sensors at high densities over a large crop field is economically and practically infeasible. And therefore, we must deploy a sensor network at strategic locations. And we collaborate with Professor Bing Yao from the University of Tennessee and Professor Jiang Xie at UVA to develop an optimal sensor placement algorithm based on active learning to identify a subset of three-dimensional locations for placing the in-situ soil sensors such that the soil moisture and salinity estimation error is minimized. And we model the random variables describing the soil moisture and salinity at any location and time as a spatial-temporal Gaussian process with sensing noise. And the set of hyperparameters in the kernel functions and standard deviations can be estimated by the maximum likelihood method based on direct sensor measurements. On top of this purely data-driven Gaussian process model, we can introduce a physics-constrained spatial Gaussian process modeling framework that incorporates the water and solute transport models. And this is combined with space filling design and the physics-based uncertainty measures to sequentially place the soil sensors. And once the sensors are strategically placed and start collecting data, we will develop an effective way to assimilate these local sensing data to characterize field scale, root zones, water, and solute distribution map. And the idea is to augment physics-based models with multi-source sensing data in the spatial temporal deep learning framework based on physics-informed neural network. And this framework implements a new architecture based on a 3D convolutional neural network and LSTM to effectively handle the spatial temporal data structure of multi-source sensing data. And we also define a physics-based loss function to estimate the hyperparameters in the nonlinear expressions of the hydraulic conductivity function as well as the water retention curve parameters based on the actual sensor measurements. And this process, this will improve the accuracy of the physics-based numerical solutions that I just described. And this process basically iterates itself to refine the sensor locations and field-wide soil moisture and salinity profiles. But last but not least, to keep the soil sensor network continually operating and collecting data, it is important that the deployed sensors are healthy and reliable, especially under situations of poor wireless connectivity and harsh weather conditions. And therefore, we're collaborating with Professor Akashdeep to effectively monitor sensor degradation, health, and replace failing sensors in an efficient manner. The idea is to develop a data-driven framework for sensor network failure prognosis and optimal multi-sensor placement. We hypothesize that even if a sensor's health status is not known due to partial observability, it can probably be inferred from its neighboring sensors. So therefore, we propose a shared representation of sensors' health through a multivariate spatial temporal Gaussian process formulation for degradation applications. And our proposed formulation is unique in the sense that it exploits the spatial and temporal correlations both within and across different sensors. Through the cost-effective management of field-scale soil sensor network, we believe that farmers will be more willing to adopt sensing technologies in their fields. So at OSU, we are blessed to have access to state-of-the-art centers and initiatives that allow us to conduct field validation studies and extension and outreach activities. For example, we're able to travel to southwestern Oklahoma and connect with and engage with local farmers, community leaders, and local extension experts through the OSU Rural Renewal Initiative to really figure out the pain points and their needs for better irrigation and soil monitoring solutions to facilitate rural community renewal. And OSU Ag Research, which operates more than 40 field and research service stations across Oklahoma, is also willing to support us to conduct experimental validation of our computational framework in one of their research stations. So hopefully this gives you a flavor of what we do in terms of promoting sustainability and digitalization of food production. So next, let me switch gear and discuss the ongoing trend of decarbonization of chemical manufacturing. So according to the DOE Advanced Manufacturing Office, the US manufacturing sector approximately uses 20% of the country's primary energy and emits 18% of the total greenhouse gases. And chemical and refining industries are the top two energy use processing industries sectors, accounting for roughly 45% of the primary energy and greenhouse gas emissions of the entire manufacturing sector. And the large percentage of the process energy used in these two sectors is for process heating. Almost all of this process heating is currently met by direct combustion of fossil fuels or through the use of steam that is raised directly or indirectly through the combustion of fossil fuels. So historically, for process heating applications, there has been a choice of whether to use heat from the combustion of fossil fuels or to convert the combustion heat to electricity and then use the generated electricity. In this case, the extra cost and the efficiency loss due to conversion to electricity had to be balanced against the synergy, process synergy, as well as the ease or inconvenience of using the combustion heat directly. However, as the US energy landscape continues to shift towards decarbonized electricity, mostly solar and wind, the energy that can be directly harvested as electricity, which makes it worth examining the potential impact of replacing combustion heat with electricity. And this critical need to decarbonize chemical process heating via electrification creates many exciting opportunities for systems engineering research. In fact, DOE has been pushing very hard in supporting and accelerating this ongoing trend, and this includes the establishment of industrial heat shot within the energy earth shots, and then the new Institute for Electrification of Process Heating, the publication of Industrial Decarbonization Roadmap, as well as the announcement of several large multidisciplinary funding opportunities. One of the key chemical manufacturing processes that attract a lot of attention from both industry and academia is steam cracking. And steam cracking is the most prevalent petrochemical process to break down hydrocarbons, such as natural gas, into more valuable undersaturated hydrocarbons, such as ethylene and propylene, which are the building blocks of nearly every chemical product that we use every day. And steam cracking units around the world produce over 150 million tons of ethylene and propylene every single year. And since this reaction is highly endothermic, a huge amount of heat is required to crack or break the hydrocarbons. And based on our extensive survey of all 26 active steam cracking units operated in Texas, the average heat duty required just for the reaction part is 87 megawatts per unit. And this is estimated that steam cracking itself consumes 8% of the total primary energy in the chemical industry. And as chemical companies are setting ambitious sustainability goals and greenhouse gas emission reduction targets, active research is undergoing to replace the cracking furnace powered by burning fossil fuel with electrified furnace. So for example, in June 2022, Dow Chemical and Shell announced that they started up an experimental facility for electrified cracker in Amsterdam. historically, for economic reasons and for the ease of use of a central boiler to produce steam to supply heat at multiple locations in the plant, fuel combustion has been the norm for heat supply in chemical and refining industries. If all of this heat was to be provided by extensive resistive electrical heating, this will actually translate to roughly 36% of the US electricity generation. Such a large power demand for just the heating applications is not going to work out. Will put a huge strain on electric power infrastructure. Furthermore, if all this additional electricity were to be replaced or were to be produced, by natural gas power plants, then due to the efficiency of the modern power plants being in the range of about 50 to 55%, the net amount of fossil fuel combusted would nearly double, leading to an equivalent doubling in the greenhouse gas emissions. One method to reduce the environmental impact of using electricity for heat is to do so with variable renewable energy, or VRE, such as solar and wind. However, the variable nature of this VRE presents a new challenge due to the requirement of significant electricity storage, as most of the large chemical plants operate 24 hours around the clock. And therefore, our vision for energy supply for process heating for the chemical and refining industries is to diversify the portfolio and have a hybrid network. For the electrified cracker, the source of electricity can be from the power grid or from the steam turbines or fuel cell, etc., etc. And we're currently working on the resulting microgrid scheduling problem to holistically model these different scenarios and optimize the chemical plant operation. Well, most of the decarbonization research has been focusing on electrifying the chemistry or the reaction part. In many chemical manufacturing processes, the most energy-intensive part actually comes from the separation. It is known that the separation processes account for 40 to 70% of overall energy consumption in chemical plants and refineries. And among all the unit operations used for separation, distillation has been the predominant choice. And today, 90 to 95% of all the liquid separations are carried out using distillation. And as you can see from all these red arrows of a typical refinery, and these red arrows are all pointing to an individual distillation column used for separation. And in steam cracking, for example, the blocks highlighted in dark pink are all the distillation processes. And it is estimated that 2.5% of energy consumed in the United States alone is used for distillation. Currently, almost all the above temperature distillation units are purely steam-driven. This provides a unique opportunity to electrify the distillation process to achieve complete decarbonization of chemical manufacturing. Our previous findings indicate that heat pump assisted distillation, which uses electricity to upgrade the heat released from the condenser and supply it to the reboiler, can significantly bypass the energy efficiency barrier of conventional steam-driven distillation. Also, compared to directly using electricity to supply heat at reboiler via resistive heating, the use of a heat pump can actually reduce the overall electricity demand by 67 to 97% for many industrial separations. In addition, the electricity demand for heat pump assisted distillation is 50 to 85% less than non-thermal processes such as membranes. And therefore, heat pump assisted distillation is quite attractive in reducing the overall energy consumption as well as the greenhouse gas emissions for fossil fuel, for the fossil fuel scenario, and energy storage for the VRE case. And despite the significant energy savings and greenhouse gas emission reduction benefits, the use of above ambient temperature heat pump assisted distillation has been actually rare. And therefore, neither the operating experience nor the method or tools needed to synthesize, design, and optimize heat pump assisted distillation systems is actually available. And this is first because the number of possible heat pump assisted distillation schemes grows combinatorially with the number of components to be separated. And so far, there has not been a systematic method to enumerate all possible schemes and identify the complete search space. And furthermore, identifying the best heat pump distillation scheme from an immense search space, as well as finding the best operating conditions, is virtually impossible due to the complexity of the resulting complex MINLP problem, let alone simultaneously accounting for the plant-wide energy integration scenarios. So recently, we successfully developed accurate surrogate mathematical models for characterizing the separation behavior of heat pump assisted distillation systems and calculating their energy requirement. And this allowed us to come up with tailored solution algorithms, bound tightening constraints, and tight relaxations to solve the complex optimization problem in terms of minimizing the energy consumption, greenhouse gas emissions, and total costs. The third reason why the heat pump assisted distillation is not widely used is because, like conventional chemical plants, electrified process units are susceptible to various disturbances and faults during its operation. So for example, for distillation operation, even slight disturbances can cause the column to deviate from the designed optimal operating window, thereby deteriorating its energy efficiency and even cause safety incidents. However, current plant supervisory and alarm management systems rely heavily on the operator's experience, which is of course limited as faults is often noticed long after it has occurred. So online plant monitoring is often tricky, mainly because, number one, fault scenarios are very complex, and number two, the sensors continuously produce massive arrays of big data streams that are often non-parametric, meaning that the data streams may not follow any particular distribution, and heterogeneous, meaning that the data streams may not follow the same distribution. So to target these two challenges, we developed a novel fault detection and diagnosis framework called FARM for fast, accurate, and robust monitoring that outperform our state-of-the-art algorithms. Unlike existing general-purpose process monitoring frameworks, our FARM's unique hierarchical architecture successfully bypasses the intrinsic trade-off between the fault detection speed and the accuracy that is present in existing process monitoring algorithms. And in terms of fault detection, we propose new multivariate statistical process control techniques for fast anomaly detection of non-parametric heterogeneous data streams. And furthermore, in this framework, plant operators can choose a user-specified false alarm rate based on their expert knowledge of the process. And in terms of fault diagnosis or classification, we're looking on building a GNN-based approach to learn the directed graph abstracted from the evolution of sensor data streams with detected mean shifts. And we believe our FARM framework can help de-risk the decarbonized chemical plant operations at the desired operating points, thereby reducing the operating cost as well as the carbon footprint, as well as process safety risks. So lastly, I would like to briefly introduce a new project that we started to work on in collaboration with Professor Paritosh Ramanan and OSU. As we discussed earlier, chemical process heating, such as steam cracking, consume a significant amount of energy, and therefore, chemical process heating must be tightly integrated with electric infrastructure system so that electrified chemical plants and refineries can jointly optimize the operations with power transmission systems. In addition, transmission operations must be coordinated, conducted in the full awareness of the predictive maintenance planning of the chemical plants, and otherwise network constraints might be violated. So as a result, one would expect power systems and chemical stakeholders to share their data in real time. However, most chemical stakeholders are unwilling to share their process data due to privacy and security liabilities. And this poses two challenges to the smooth integration of electrified process heating with transmission systems. First, jointly optimizing the operations of chemical plants and transmission system stakeholders is difficult. And second, coordinating predictive maintenance of chemical plants jointly with the power system organizations is very challenging. So to address these challenges, we propose decentralized methods as privacy-oriented alternatives that eliminate the data sharing obstacles and help smoothly integrate electrified chemical process, heating, and clean energy systems. We hope the results from this project can break down the barriers for information sharing that is impeding the decarbonization efforts for chemical process heating via electrification. So with that, I would like to acknowledge funding support from NSF and the OSU Cowboy Innovations. I would also like to thank Fractionation Research, Inc. For being in our industrial partner. And most importantly, I would like to thank all my graduate students. Saba worked on the stochastic optimization of agrochemical supply chain network, and she's currently working on the microgrid scheduling problem for decarbonized chemical plants. And Ali Raza, he is working on the online process monitoring and optimal control of batch crystallization processes. And Zheyu is working on the data-driven physics augmented in-situ soil sensing. And Magdad is working on the computational fluid dynamics and its applications in chemical leakage detection. So with that, I would like to thank you very much for your time, and I'll be happy to take questions. Thank you.
Thank you very much, Dr. Jiang, for a nice presentation. Are there any questions?
This is a really interesting presentation. Thank you so much for coming and visiting. It's good. I assure you our weather is often like this, so
yeah.
please come back.
Yeah, I'm impressed.
I had a question mainly regarding kind of industry standards around chemistry and for chemical industry. One other component that perhaps is worth commenting on is around kind of, are there working groups that are establishing kind of greater transparency in terms of like energy usage that down the line kind of may play into kind of moving what you propose even further?
Yeah, definitely. I mean, that's a long ongoing trend, right? Otherwise, this decarbonization won't happen very easily. Currently, there are big companies working together. For example, Dow and Shell, they build electrified cracking furnace together, right? So I'm sure that discussions and dialogues are ongoing to make sure that these kind of research R&D efforts are transparent, as well as their operations. But R&D could be transparent, but the operation is another thing, right? So operations is related to their profit. So they typically tend to not willing to share this information, even across different plants within the same company. So I mean, there is a lot of barriers that we need to overcome in order to achieve that. But I mean, this is definitely an ongoing effort, and people, a lot of things comes to the mindset change, right? So we need to persuade the chemical stakeholders to realize the importance of information sharing. And I believe that the decentralized algorithms offers such a way of privacy-oriented solutions. But thank you, that's a good question. Yes?
Do you have an outreach program? Because I've seen in agri-tech, the main problem is that there's a lot of inertia with farmers and they are not ready to experiment with technologies until it is robust and proven. So how do you convince that, how do you convince farmers to let you experiment on their fields or maybe adapt a technology for future use?
Right, that's a very good question, and I think that's precisely why we need to do this, right? So OSU is a land-grant institution, right? So it has a very deep connection with local farmers and local communities. So we have workshops every year that allows farmers to connect with researchers on irrigation-related topics, on rural renewal-related topics, on healthcare, lots of things. And to persuade them to use the technology, we first need to have a validated technology in our lab, right? So we're currently working with the OSU Ag Research. So they have a lot of land, like they have more than 40 research stations, and the land is like millions of acres, and they're willing to basically spare land for us to do whatever I want, and then just try our computational framework and see how it goes, right? And then once we have the data, I think the data is the key, right? So once we have the data, we can prove to the farmers that this does work and try it out. I think another thing is raise awareness. Like the extension programs and the outreach programs are there to help farmers realize that this is a problem. Because in a lot of cases, for example, irrigation scheduling, farmers, they don't realize that this is an issue. Like they were actually telling me that they just, for example, for center pivot irrigation, they just keep the water on for for days and never stop. And the reason is because they don't know the other way. Like there is no other way that they can think about. So allowing them to explore alternatives, we first need to make them realize that alternatives exist. So I think the extension programs, outreach programs are established to do that, serve that goal as well.
Thank you once again,
Yeah,
Dr.
thank you
Jiang,
very
for
much.
your nice
Yeah,
presentation.
thank you for your time. Thank you.
Cornell Engineering Systems Engineering.